liquids, but of course, like fundamentally, they're not the same because like transfer from liquid to liquid. Of course, it's not the same as from gas to liquid or liquid to gas. So in the liquid extraction is based on the difference in solubilities. In order it to work, we have to select a solvent. Okay, so first you have two streams. Stream of diluent with the solute and stream of solvent. Maybe originally without a solute, but like after the process, the solvent is gonna extract the solute from the diluent stream into the solvent stream. Okay, so of course we want to select a solvent that allow a better solubility of solute. And okay. Yeah, so we want to pick a solvent that allow a better solubility, so that the solute can transfer from the diluent to the solvent. And ideally, we want the two liquids to be immiscible, meaning they don't mix with each other. Okay, like they don't interact with each other, don't mix with each other. But of course, like in real life, in some other liquids will be immiscible. Maybe they can each other a little bit. I'm sorry, but Miss, I don't know, Yanada, can you turn off your mic? Like I can hear that. I can hear the noise.
เปิดแล้วค่ะ
Your mic still on. So if you don't know how to turn it off, I'll turn you off myself then. Okay, so so again, like we want to transfer the solute from one liquid to the other liquid, and if possible, we don't want the two liquids to be mixable. Like we don't want them to interact with each other. But of course, like in the real life, like some of them will be mixed with each other a little bit. And the solvent that we use, we want to recover it later, like to save cost, to be able to reuse it again and again. Okay. And since in this technique, in this process, we don't need to use any vaporization. We don't need to apply any heat. So this process can be done at low temperature, and you don't need to use a lot of energy for this process. And this is like one example of the process that you can see it in chemical plants. Just like in absorption and stripping, usually absorption and stripping goes together, right? Because we want to be able to reuse the solvent liquid. Here also we have like a solvent recovery unit, so that it's like reuse and recycle. The solvent can be used again and again. Okay, and usually they say that the solvent recovery step is even more extensive than the actual extraction by itself. Okay, so yeah, actually this part is more extensive than the main extraction unit. And there are many types of extraction units that we can use. These are some examples, different types. I'm not gonna go into detail, but like you can look up this table. Like each type of extraction unit has like pros and cons. Depends on your budget, depends on how difficult it is to do the extraction. So depends on the types of chemicals that you work with. So yeah, you can look it up and for your own information. And also like also depends on how many equilibrium stages are required for your process. Like if if your process only require a few equilibrium stages, maybe a simple one like mixer settlers can be used. But if like it requires many stage of equilibriums, then maybe like use one of the system with mechanical part that allow a better what is it like higher contact between two phases to promote the mass transfer, maybe like to give a better result. And ideally, when we select the solvent, we want it to be highly selective for the desired solute, okay, and not selective to the contaminants, okay. Like in our ideal problems, we only have like three compounds, right? The solvent compound, the diluent compound, and the solute compound. But of course, in real applications, you're gonna have like a bunch of chemicals, like maybe tens or hundreds in your feed, right? And that there may and the feed may contain some contaminants, some undesired compounds. And if possible, we want our solvent to be very selective, only dissolve and extract the solute that we want, and not other contaminants, right? Like we want it to be as highly selective as possible. And so then we have to consider something called the selectivity. Okay, the selectivity alpha. We want the selectivity value to be as high as possible, like to get the most of the solute that we want. And also, we try to use the solvent that immiscible to the diluent, right? We don't want the diluent and solvent to be mixed with each other, but it can sometimes in real application it cannot be avoided, right? So if for some reason after the process you get a mixture of solvent and diluent, you would want they to be easy. You want they both to be easy to separate from each other. Like maybe use settler to settle down one of the liquid out of the other liquid. Okay, so basically, ideally, we want the two liquids not mixed with each other. But if you cannot avoid it, then the next best thing would be to be able to easily separate these two. Okay, so maybe you cannot avoid the mixing, but if possible, we want these two to be able to separate from each other easily. And also the solvent, it should be non-toxic and chemically stable, environmental friendly, and cheap, and it's inexpensive. Okay, so these are other considerations. And when we want to select like a good solvent with large selectivity, we will consider something called solubility parameter delta. Okay, from this equation here. So like you can look up like from literature or textbooks to look for the values of delta. Okay, and so let's say you have like liquid A and liquid B. If the values of deltas of A and B they are close to each other, it means that they are likely miscible. Okay, if the two values are close to each other, means that they're easy to mix with each other. Okay, like for example, if the delta values of water, ethanol, and benzene are these. Okay, so the water is 23, ethanol is 12, and benzene is 9. So the water and ethanol they are miscible because like the values because they are close to each other, right? The values and the ethanol and benzene they also miscible because like the values of delta they are close to each other. But the water and benzene are immiscible because the delta value of water and benzene they are quite far from each other. so they don't mix with each other. Okay, something like this. Something like this, like the delta values can tell you whether or not the liquids, the two liquids are miscible, are easy to mix with each other or not. Okay. And other thing like the environmental concern, like nowadays, like there are many techniques. There are many techniques to use in with liquid extraction. Like in the past, people use like chlorinated solvent, uh, and uh, and also maybe like the hydrocarbon solvents, and these are quite toxic and they are not environmentally friendly. Okay, so there are like other new type of solvents that people consider, and maybe they are like new, basically like they are new generation of liquid extraction, like ionic liquids or like supercritical extraction. So yeah, so these are new solvents to consider, like better than like traditional solvents that are not environmentally friendly, not environmental friendly. Okay, so these are like better choice for environment. Okay, next, yeah, let's get into like how to solve, like how to do the calculation. So one of the simple process that we're going to consider is the counter current. Okay, counter current unit with a diode solute. Okay, so yeah, as you know, just like similar to previous chapters uh, in absorption and stripping, like if you have low concentration of solute, it's gonna make our calculation easier, simpler to solve. Okay, and that's what we are dealing with here. So in the counter current, just like the name suggests, right? Like the two flows, they pass each other in opposite directions, and we will assume that the two liquid phase that leave the stage, they are in equilibrium. Okay, like the two liquid streams that leaving the stage, each stage they are in equilibrium with each other, and usually okay, so at the beginning, not usually, at the beginning, like we have solute A dissolved in diluent D in the feed, right? And we want the solute to transfer from diluent to the solvent S. Okay, so in order to prevent the mixing of the solvent to the diluent, usually we want our solvent stream to be pre-saturated with diluent. Okay, pre-saturated mean that is maybe we like like try to mix the solvent and diluent together as much as possible before we use in the system. This way, when the solvent is already saturated before entering the system, then during the system, the solvent is not gonna take it's not gonna take up more of the diluent because the solvent is already saturated. Okay, so we do the pre-saturation to prevent further mass transfer of diluent into the solvent. We only want the mass transfer of the solute from the diluent to the solvent. Okay, so that's why it's pre-saturated here, and we also have some like some new terms to call the streams here. So the stream with high concentration of diluent, we're gonna call it raffinate. Okay, and the stream with a high concentration of solvent, we're gonna call it extract. Okay, so basically raffinate is diluent plus solute, let's say A. Okay, and the extract is the solvent plus the solute A. Okay, that's how we define raffinate and extract. Okay, so the two streams that flowing in opposite directions, we call them raffinate and extract. Okay, raffinate is raffinate is the diluent with the solute, and the extract is the solvent with the solute. Okay, and just to show you all the variables that's going on inside the unit. Okay, in the process, in the extraction unit. So these are the variables that we care about. And then just like in absorption and stripping, we can use the Mackay field to solve this problem. Okay, and so we're going to plot a equilibrium curve. Okay, and the energy balance basically for the energy balance we're not gonna we're not gonna care much about this because we're gonna assume like like constant temperature, constant pressure, and no heat of absorption, no heat of like solubility, no heat. Yeah, so basically we're gonna focus more on only focus on the mass transfer. Okay, blah 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 blah. I'm gonna just we assume isothermal and isobaric. So we don't care about energy balance, and usually when these assumptions are true for dilute system, our operating line also will be straight. Okay, our operating line will be straight here, and also if we say that the diluent and solvent they are totally immiscible, right? They don't mix with each other. Then the flow rate of diluent and solvents they're gonna be constant. Okay, because there's no mass transfer from diluent to solvent and solvent to diluent. There's no mass transfer between two phases, right? Then it means that the flow rates of diluent and solvent should be constant. Okay, but these flow rates do not include the total raffinate extract. Okay, just like I defined here. Okay, raffinate is the sum of diluent and solute, and extract is the sum of solute and solvent. Okay, even though we say it right here that diluent and solvent they are constant, but it doesn't mean that R and E also constant, right? Let me say it again. So I am saying right here that we say that the diluent and solvent they don't mix with each other, right? So they don't have mass transfer between two phases. So we can say that D and S are constant, but it doesn't mean that it doesn't mean that the raffinates and extracts are constant. Okay, they're not they don't have to be constant. Okay, R and E they don't have to be constant, even though D and S constant, because R and E the raffinate it does not contain only the diluent, right? It also contains the solute, and the extract doesn't contain only the solvent, right? It also contains the solute. So if there's a mass transfer of solute from raffinate to extract, right? Then the total raffinate and extract stream they don't have to be constant, right? Okay, so because there's a mass transfer of the solute from raffinate to extract. Okay, so R and E they don't have to be constant. But if we say that our system is very dilute, okay, so it's very dilute, like the amount of solute, very small, like the amount is very small amount. Then you can say that roughly equal to FD and E is roughly equal to FS. Okay, because like the amount of solute is very small, right? Then you can like approximate it and say that the raffinate flow rate is about the same as the diluent flow rate, and the extract flow rate is about the same as the solvent flow rate. Okay, because the solute is very small. Okay, and then next you can write out the mass balance the mass balance right, and then you get this, and then for the mass balance you just rearrange a bit to get the operating equation like this. Okay, and since we assume r is to be constant, then like you can again, just like previous chapters, you can draw this operating equation on the magnetic field. Okay. And then for the equilibrium data, we can use something called distribution ratio KD. Okay, so this is our equilibrium line. Okay, equilibrium equation. So just like in previous chapter, we're gonna draw the operating line and equilibrium line on the magnetic field. Okay, and again, so just to emphasize that for our calculation, we deal with dilute system, right? When for dilute system, the KD is constant, but at a higher concentration, KD is often a function of concentration. Okay, so so we say that KD is constant. It only works when our system is very dilute. Okay, so just keep that in mind. And this table right here just to show you an example of like like different different values of KD for different types of liquid extraction system. Like different type of solute, different type of solvent, different type of diluent, and also at different temperatures. Okay, so you have to so this one show you an example, and if you know which solute, which solvent, which diluent to use, and which temperature to use, then you can look at the table to get the KD value and use this KD value like to derive the equilibrium equation and draw it on the magnetic field graph. Okay. And actually, from this table, it's kind of tell you something interesting. Okay, so you can see that these values of benzene, they are quite small, right? Oh, sorry. Okay, like okay. So yeah, these value of KD, they are quite small, right? So it means that the benzene is not a good solvent for acetic acid, right? Because these KD are quite low, and but then the water, so it's gonna be the opposite. Okay, then if the KD values here, when we use benzene as a solvent, you get small values of KD, right? So then the opposite will be true. Then the water would be a good solvent if benzene were the diluent instead. Okay, because like these KDs are for when the benzene is solvent, right? And they are low. Like these KD values are low. But if you use the water to be solvent instead, then the KD value is gonna be high. It's gonna like the reciprocal of this value. Okay. And from this table you can also see that 1-butanol is a much better solvent than benzene, right? Because this is when you use 1-butanol as a solvent, you get a much higher KD compared to when you use the benzene. Okay, and also this is just something you should keep in mind. Benzene is also not a good solvent because it's carcinogenic. Okay, basically it can cause cancer. Okay, so yeah, benzene is one of like kind of dangerous, toxic hydrocarbon solvent. So if possible, you want to avoid using it. Okay. And be careful here. KD is not dimensionless. Okay, it has a unit of extract to per raffinate. Okay, so even though it's like mass per mass, right? Like gram, like the ratio of mass show up different types of compounds. Okay, so they are not dimensionless. So just be careful here. Like beware of the units. Okay, be careful the units. Don't use it wrong. That's the message here. And also KD in terms of weight is not equal to KD in terms of moles. Okay, so you have to be careful when you do the calculation. You have to know whether or not the values of your y and x they are in terms of weight or they are in terms of moles. Okay, because the composition in terms of mole and the composition in terms of weight will use different values of KD. Okay, and KD and again KD is not exactly a constant. Okay, it also depends on like temperature, pH, and presence of other chemicals. So keep this in mind. KD is not exactly a constant. Okay, and there's an optimum temperature to get like the highest KD. Okay, so like for example, this one right here. This gives you the highest value, right? At 40 degrees Celsius. Okay, so in this system, at the temperature of 40 it gives you the best result, the highest KD. Okay, so also in other system you have to maybe if you want to get the most extraction to get the best result, you have to check the temperatures. Okay, so like check to see at what temperatures you get the best result. Okay, not just any temperature if you want the best result. So with this technique also like extraction process often use the chip intermediate of pH to extract and recover solute from the solvent. Okay, so because different temperature or even different pH can give you like different values of KD, right, and different solubilities. So in the real application, people use this knowledge to manipulate, to control the extraction process. By shifting and changing the temperature to get, like to do some extraction and recovery. So basically this is a high technique of like extraction process control. Okay, you can use like temperature and pH to manipulate your process to get it works as you want. Okay, so let's look at example here. This one, like is a counter current, right? And it wants to extract acetic acid, like from water into butanol. Okay, so our solute is acetic acid, and our diluent is water, and our solvent. Okay, this is acetic acid. Again, acetic acid is our solute. Water is our diluent. Solute A, diluent, and butanol here is our solvent. Okay, so we want to transfer of acetic from water to butanol. This problem is a little tricky because of this stream right here. Okay, usually you're not gonna have this. Okay, usually you will only have like two streams going in and two stream going out, right? But in this one you have this middle feed here, and it makes our system a little more complex. Okay, with this feed going into the middle, you're gonna have two overlapping lines. Okay, so this one is equilibrium. Okay, this one is equilibrium, but you're gonna have two overlapping lines here. This one right here and this one right here. Okay, two overlapping lines. maybe obliquing y1, obliquing line 2. Okay, so because of the feed, you would have two obliquing lines. So it makes our problems a little more complex. Okay, so with two obliquing lines, you're gonna have two values of slope, right? So for the top one, this is the slope. Okay, and for the bottom one, this is the slope. Okay, so yeah, you have the solvent going in here at 44, right? And then you have another solvent here at 30. So that's why in the end you get 74 here. Okay, and then yeah, from the KD table, the KD is 1.613. So this is the equation for the equilibrium line. Okay, and then yeah, and then you can find the obliquing line equation, and for the bottom the slope is this. Okay, the slope is r bar over e bar, so 100 divided by 44. Okay, yeah, the bottom obliquing line go through this point. So the slope, 1 point, then you can draw the line, right? And then for the top, for the obliquing line, okay, so this is obliquing line 2, and then for obliquing line 1, okay, so you have this slope here, r over e. Okay, so then the slope of obliquing line 1, right? What you need to know next is just 1 point. Okay, we want to draw the line for obliquing 1. So we get the slope. Then next you want to find a point, 1 point for obliquing line 1. So then you can draw the line for obliquing line 1. So what we use is this here, the horizontal line for the feed. Okay, for this feed. Okay, for this feed right here. Okay, so yeah, you can use the horizontal line, this line right here. Okay, and then at this line is gonna intersect. Let me clean this up a little bit. Okay, so this right here, yeah, actually the intersection is here. Okay, so this line is gonna intersect with this line at this point, right? We know the obliquing line too, right? From our work here. Okay, because we know the slope here, and we know this point here. Okay, then from this you draw the obliquing line too, and you draw the feed line here. This feed line is for, it comes from like the feed that goes into the middle of the column. So you get the intersection here, and you know that this obliquing line 1, they also have to connect to this point here. Okay, so we use this intersection. Okay, we use this intersection and the slope 1.35 to draw this line. Okay, to draw this obliquing line. Like the slope, you know 1 point, right? Then you can draw this line, and that's what we did here. Okay, so you get the obliquing line for OP1. Okay, and then you can you can also use the overall mass balance to find y1. Okay, yes, to find this point here. also use the like if you don't want, basically there are two ways. There are two ways to draw this line. Okay, like use this intersection and the slope. Okay, that's one way. The other way is to use the overall mass balance, just like this one right here, to get y1. Okay, to get y1. Once you know y1 and x0, right? Then you also know this point. Okay, you also know this point, and you know the slope. Then you can draw the line here. Okay, so there are two ways to draw overlapping line one. The first way is to find the intersection here and use the slope. The second way is to find this point here at the slope. Okay, either way you can draw this overlapping line OP1 here. And then once you draw these two lines, overlapping line for OP1 and overlapping line for OP2, then you can draw the steps. You can draw the steps and then get that the equilibrium context is about 11.8, which is about almost 12. Okay, so that's how you do it. Again, this problem is a little bit complex because of like the feet in the middle. Okay, but yeah, as long as you stick to the procedure, draw the equilibrium line, draw the overlapping lines, then you can use the magnetic field and then find the number of stages. Actually, this is something that I want to emphasize. Like your friends, when they show you guys how to do the exercise using like Clemson equation, like the Clemson equation, you definitely cannot use that. You cannot use Clemson equation with this problem here, because for the Clemson equations, your column only have like outlets and inlets at the bottom and the top. Okay, they don't have like the feet in the middle of the column, like this example right here. So in this example, you better off with the magnetic field technique, graphical technique. You cannot use like Kempsel equation. Okay, because Kempsel equations is only work when you don't have the feet in the middle, when you only have outlet and inlets at the top and the bottom. So you cannot use Kempsel equations here. You only use the magnetic field here. Okay. So yeah, keep that in mind. Yeah. So the magnetic field is like similar to the dilute stripping. Just like similar to last chapter. So in this case, you can see that like the equilibrium is above, is upper, and the opposing lines are lower, right? Like the equilibrium line is above the overlapping lines, just like in the stripping, similar to the stripping. However, like of course, like in the stripping is the mass transfer between gas and liquid, right? But in this case, it's from liquid to liquid. So the mass transfer characteristic and the flow dynamics, they are different. Okay, so fundamentally they are different, but the calculations they are quite similar. But anyway, because like of these difference in mass transfer and flow dynamics, so like the state efficiencies and the column diameter sizings, they are different. So then when you decide the columns for the liquid extraction, they're not gonna be the same as when you decide the column for stripping. Okay, so just keep that in mind. But in stripping, you have maximum L over G, right? Or L over V. L over G or L over V, up to you how to use it. So the same, like for extraction, you also have like maximum R over E. Okay, and at this point, it can also be determined in the same way. So let's say okay, yeah, let me just draw. So then this is equilibrium, right? And you have maybe like operating line here. Then if you want to get like maximum R over E, so it's gonna look something like this. Okay, so and this gives you maximum R over E. Okay, so this is gonna give you maximum R over E. Just like similar to stripping. Basically, it's similar to stripping. So maximum R over E give you like minimum solvent flow rate, right? And with infinite number of stages. Okay. So like E mean is like the minimum solvent flow rate that you can go. Okay, you cannot go lower than this. Okay, even at this point, like theoretically, it means that you use infinite number of stages. So this is like theoretical limit, basically theoretical limit for your liquid extraction. And if like if the question give you the number of stage instead, and the outlet raffinate concentration is unknown. Okay, so in this case, you have to use trial and error. Okay, just like in stripping, if the number of stages is given instead, and you don't know the outlet raffinate concentration, then you have to guess some value. Okay, guess the outlet raffinate concentration here, and use the specified number of stages for your calculation, and you have to guess and check if like your guess value is correct or not. Okay, so yeah, just like in stripping. And also again, similar to stripping, if you have like if you deal with multi-component extraction, like you have multiple solutes in your system, okay, then you may assume that each solute is independent and do the calculation one solute at a time. Okay, do a calculation one solute at a time, just like when we deal with multi solutes in the previous chapters. Okay, do calculation for one solute at a time. Okay, but of course, again, this technique only work when you have very dilute, very dilute solute. Okay, very dilute solute. Okay, so yeah, it's quite similar to stripping. Okay, and next, but this is something different from, this is kind of unique to liquid extraction. So, so in the liquid extraction, is it unique? Okay, yeah, in liquid extraction, you can also have something called closed flow extraction. Okay, just like in this picture here, like you have multiple streams of solvent. Okay, you can have like multiple streams of solvents. Yeah, that close flow to your raffinate. Okay, so multiple streams of extract, and you're gonna have mass balance for each stage. Okay, you're gonna have mass balance for each stage, because each stage has different operating equation because of the slope is this one, right? You can see that EJ, like E for each stage, they don't have to be the same. Okay, E for each stage, they don't have to be the same. When they are not the same, then the slope is not the same. When the slope is not the same, it means that you have different lines, different operating equations. Okay, so yeah, this is how the graph's gonna look like. Like say in this example here, I think they have 3 stages. Okay, they have 3 stages for, and then they have hold on a second. Yeah, three operating lines for each stage and three slopes, three slopes for each stage. And so you start, the way you do it is, of course, first you draw the equilibrium line, right? You draw the equilibrium line, and then you start with this point here. Okay, start with this point here. You know the slope, right? Then you just draw the operating line for this stage here. Okay, and then next, this point, like the problem should tell you. Okay, the problem should tell you like information about these points. And then next, you use the information about the slope of the next operating line, and then draw this line here to hit with the equilibrium line. Okay, so this is like a straight line down to connect to the next point, and then draw another line here using this slope here. Okay, so yeah, that's how you do it. So this is the direction when you draw the line. Okay. Yeah, so the procedure is repeated until xn is reached. Okay, so this is our xn here. This is the final composition. Okay. So in this example, they have like 3 stages. Again, so each stage can have different flow rate. Okay, each stage can have different flow rate, and also can have different mass fraction yj in. The problems have to specify these values for you. Okay. Yeah, these lines are similar to finally legislation, and for the cross flow system, the two outlet stream they are in equilibrium, then they are also on the operating line. Okay, unlike the counter current, for the counter current, two outlet, they are in equilibrium. Okay, hold on a second. Two outlet they are in equilibrium. Okay, for the counter current, but they are not on the same, not on the operating line. Okay, for the counter current. Okay, for the counter current is gonna be yj plus 1 and xj, right? For the counter current, it's gonna be yj plus 1 and xj that are on the same operating line. But for cross flow, is yj and xj. Okay, do you see the difference? Again, like let me say it again. So for counter current, yj plus 1 and xj, they on the same operating line. But for cross flow, it's gonna be yj and xj. Okay, so that's the difference between cross flow and counter current. Okay, and again, like if you deal with dilute multi-component, you can do each solute is independent from each other. So do a calculation for one component at a time. Okay, and again, if the number of stages is specified, then you have to do the trial and error. Like guess the output composition, and use the number of stages to solve, and check your answer if it's the same as the value that the problem gives you or not. Okay. Okay, so yeah, this example right here is the crossroad. This one is a little confusing because XF not given. Okay, this one XF not given. It doesn't say. XF. Okay, XF. It doesn't tell us. But we don't need to know. Okay, we don't need to know because the question asks for the recovery fraction. Okay, the question asks for recovery fraction. Okay, this recovery fraction you don't need to know XF. Okay, because eventually XF is going to be cancelled out. Okay, so maybe like for some of you when look at this problem maybe a little bit confusing, like if XF is not given, then how can we solve the problem, right? But you don't need to know XF. Okay, because the problem just asks for the fraction. Yeah, XF is not specified, but we don't need to know it anyway. Okay, and then KD is given, right? KD is given, so you can find the equation for the equilibrium. Okay, so this one right here is the equilibrium. Okay, and then we just say y it is equal to 0 because we use pure. Okay, we use pure solvents here. Okay, use pure solvents. So it means that y for both solvents they're gonna be 0. Okay, because they are pure. And and we know E1, so we can find the slope. Then we can find the overlapping line for stage 1. We got this. Okay, so we don't know XF. We don't know XF. We just leave it as it is. Okay, we just leave it like that. And then we solve. For x1 and y1. Okay, we solve for x1 and y1. Using the equilibrium and overlapping equations. Okay, using this information, then we get x1 and y1 like this. Okay, so we don't know XF, we just leave it like that. But as I said, like because the question just asks for recovery fraction, and recovery function for stage 1 is y minus x1 over xf. Okay, so you just like put in x1 here, and then xf is going to be cancelled out, and then you got the answer. Okay, so as I said, like you don't need to know xf here because xf is going to be cancelled out. Okay, and then for stage 2, you find the overlapping line for stage 2. Okay, using the same concept, like RE2 R over E2 is the same as R over E1, which is equal to 2. Okay, and then so this is the equilibrium line, equilibrium equation, and this is the overlapping equation, like to solve for y2. Okay, so then solve, and then you got these values. Okay, and then again put in the equations here, and then xf is gonna cancel out, and then you got the answer. Okay, so yeah, you have case 1 and case A and case B here. Case A, you only have like for case A, you have only a single stage, right? Single stage means that you don't consider this. Okay, you only have single stage. But then for case B, you have both stages. and yeah, this is what we get. Okay, single stage give you this, and then if you use like two stage, and then the second stage give you this. Okay. Yeah. So again, this one is a little tricky because XF is given. XF is not given, but you don't need to because the question asks for recovery fraction, so XF is going to be cancelled out. Um, yes, and for linear, for linear equilibrium and orbiting lines, analytical is easy because when they are linear, they are straight. So when you draw the lines, um, well, okay, if if your problems have linear equilibrium and orbiting lines, then you can use analytical solution, meaning you don't have to use a graphical technique. Just like your friend, when the group that present on exercise problem two, when on exercise two, they use analytical technique. Yeah, so from okay, wherever. So yeah, they use analytical technique, and it's quite okay, right? But be careful if your problem have the curve equilibrium line. Okay, have the curve equilibrium line, then the magnetic field is easier. Okay, so it's good for you if you can master both techniques. Like analytical technique and the graphical technique. Okay, you should be able to do both. And if you compare the results of uh, cross flow here with a counter current, it says that the counter current is gonna have a higher recovery. Okay, because it gives you a higher recovery because in the counter current the solvent is reused. Because like you only have one inlet of solvent, right? In counter current you only have one inlet of solvent, and the solvent is gonna be reused in each stage. When cross flow you use fresh streams of solvent for each stage, right? So solvent is not reused in cross flow, so you're gonna get a higher recovery with the counter current. Uh, yeah, so the reuse of solvent result in more separation in counter current than the cross flow. Okay. The counter current, also give you high purity and high recovery. Okay. For the cross flow, you have to choose. You can only choose either high purity or high recovery. Okay, so you cannot get both for cross flow. Like for counter current it can give you both. So counter current give you a better separation. But then and sorry, this is wrong. It has to be cross flow here. Okay. So yeah, I typed this slide here is wrong. It has to be cross flow system. Okay. So you may think that the counter current is better, right? Because I just said that counter current give you both high purity and high recovery, while for the cross flow you can only choose one. You cannot get both. Okay, so counter current give you a better separation, but cross flow system have an advantage. Because like in counter current system, there's also maybe like a problem with the flooding. Like you can get flooding problem easier with the counter current than with the cross flow. Cross flow has less problem with the flooding, and also if because in the counter current more there's a more mixing. Like there's a higher mixing of like two liquids. Okay, there are higher mixing between diluent and solvent. So eventually you want to separate more liquids, right? So maybe you have to use settler, use settler to separate two liquids. And with the cross flow, there are less mixing between the two liquids. Then you're gonna have less problem of like settling of the two liquids. Okay. So basically, what I want to say is that like there's a pro and con. There's a pro and con between cross flow and counter current. For the counter current, you get a better separation, but maybe you have a more problems with the flooding and slow settling. Okay, so yeah, that's what you have to keep in mind. But anyway, and also in estrogen stripping, if you want to apply like cross flow in estrogen stripping, like in the previous chapters when we in the lecture we only talk about counter current, right? In the last chapter we only show examples of counter current. We didn't talk about cross flow, but it's also possible to do cross flow and in estrogen stripping. And maybe if you have like big problem with the pressure drop with a counter current technique, then maybe you want to consider cross flow instead. Like cross flow system will have less problem with the pressure drop, less problem than the counter current. Okay, so maybe keep that in mind. But again, less problem with the pressure drop, but also less separation, like like lower performance. So you have to think about pro and cons when you decide what kind of units that you want to use. Okay, and next, concentrated immiscible section. Okay, so so far, like in the previous sections, we assume dilute, right? We assume that our solute only exists in the system in small amount, small quantity. So like it makes our life easier with the calculations. Like the lines are straight and the drawings are the lines are straight and it's easy to do the calculation. But of course, like sometimes you have to deal with like concentrated solute, right? And when you deal with concentrated solute, then you have to reconsider some of the assumptions. Okay, so in the diluted system, we say that raffinate is equal to diluent, right? And extract is equal to solvent because solute is very small. But in this case, when you have high concentration of solute, these assumptions are not valid anymore. Okay, they are not valid anymore. We can still assume that the diluent and the solvent, they are immiscible, they don't mix with each other. But we cannot say that R equal to D and E equal to S. We cannot say that anymore. Okay, so we have to like use the different types of variables. Okay, so we have to use like big X and big Y here. Basically, there's a ratio of solute to diluent and solute to solvent. Okay, like in the small X, in the small X, where can I write it? Like small X and Y, we use hold on. In the small X, we use solute over solute plus diluent. Okay, and small Y is solute over solute plus solvent. Okay, that's small x and small y. But for x and y, is solute per diluent only, no solute. Okay, and then for y is solute per solvent. Okay, not including the solute. Okay, so small x and small y, they are different. Sorry. Yeah, so for concentrated system, you have to define the new big X and big Y, okay, and also different form of operating equation. Okay, so basically and also the equilibrium data, they must be in terms of weight or mole ratios, not fractions. Okay, so be careful here when you are dealing with concentrated system. Okay, use weight or mole ratio, not fractions. Okay, they are not the same. Okay, they are not the same. But the procedure is somewhat similar. You know, like you plot the equilibrium data, plot the point past the opening line. You know, and then you can find y1 at x0, and then you can step out stages. Okay. So the mechanics feel somewhat similar to before, but it's just that the variables are different. The equation for the opening line is different, but the technique fundamentally is the same. Okay, but the equations are just different. And in the case that there is some partial miscibility, okay, when like the diluent and solvent maybe mixed with each other a little bit, the market field can still be used if we assume that the concentration of solvent in the raffinate and concentration of diluent in the extract, they are both constant. Okay. You can only use market field when this statement is true. Okay. So you can still use market field, the graphical technique, if this statement, this assumption is true. Okay, when the concentration of solvent, So FD is constant, FS constant. Okay. Okay. Getting to this point, I don't know if how many you guys still with me, but this one is probably not the most, but one of the more difficult section in this class. Okay. Like in the previous sections, we only focus on the solute, right? And we just kind of ignore the solvent and diluent because we say that the diluent and solvent they don't interact with each other, right? They just they don't mess with each other, and when we only focus on the mass transfer of solute from diluent to solvent. Okay, but there's a system that sometimes the two liquids, the diluent and solvent, they also mix with each other, and they mix with the solute. So basically, the three components, they mix with each other. Okay. So for this partially miscible system, you have to consider for this partially miscible ternary means 3. Okay, because you have like three components in your system here. This one is going to be a bit complicated because, let me say it again, in this partially miscible system, the solvent and the diluent, they also mix with each other. They have equilibrium with each other, and also equilibrium with the solute. Okay, so the three components in the system, they are in equilibrium with each other. Okay, so to solve this problem, you have to be able to understand and construct the triangular diagrams. Okay, so for the three components, the triangular diagrams, there are two types. Okay, right triangular or equilateral triangular. Okay, but for our class here, I'm gonna focus only on the right triangular because it's a bit easier to understand. Okay, but there's also like equilateral. Like equilateral means like three sides they are equal. Okay, equilateral. Okay, but we're not gonna be worried about this. We're not gonna worry about this. Okay, we only focus on the right triangular. So you have to be able to read the diagram. Like if you read in this direction, like for component one. So at this point, it's gonna be like 0% component one and 100% component one. Okay, so when you read in this direction, and then when you read in this direction, it's gonna be for component two. Okay, so it's 0% here. Oh, not 0%. Sorry. No, actually it's the other way around. Sorry. So this way. So for component two is 0% here, and then 100%. Okay. And then for component three is this way, is 0% and 100%. Okay. So you have to be able to read and to construct the right triangular diagram. Okay, so you'll be able to read it. Just like example here. So this one is water chloroform acetone. Okay, so let's say at this point right here, you're gonna have 100% acetone, 0% chloroform, and 0% water. Okay, at this point, 100% acetone, 0% water, and 0% chloroform. And this point, you're gonna have 1%, 100% water, 0% chloroform, and 0% acetone. Okay. At this point, 0% chloroform, 0% acetone, and 100% water. And then this point, you're gonna have 100% chloroform, 0% water, and 0% acetone. Okay. Again, this point, 100% chloroform, 0% water, and 0% acetone. Okay. So that is that. Then so in this case, we gonna say that acetone is solute, and chloroform is solvent, and water is diluent. Okay. Actually, just for this example, but in another system, it can be the opposite. In another system, the chloroform can be diluent and water can be solvent instead. Okay, and the feed is gonna be acetone chloroform mixture. Okay, it depends on your system. Like the graph, the triangular diagram is gonna be the same, but it depends on how you. It depends on your system. Which liquid is diluent, which liquid is solvent. It depends on you. Okay, but in this example right here, we're gonna say that the acetone is solute, chloroform is solvent, and water is diluent. Okay, so then from the equilibrium data, you need to be able to draw this something called solubility envelope. Okay, from equilibrium data, like from the equilibrium data table, you need to be able to draw this curve. It's called solubility envelope. Okay, so like this line separate the 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 triangular diagram into two zones. Okay, this zone and this zone. Okay, there are two zones here. So in this zone, it's gonna be one phase. Okay, this phone is mean one phase. One phase means that a single phase means that like everything is miscible. Okay, so in this phase, both both chloroform and water, they will be mixed with each other. Okay, they be like mixed with each other. They don't separate. Okay, in this zone. But then in this zone right here, in this zone you're gonna have two phase. Okay, you're gonna have two phase. The chloroform will be one phase, and the water will be one phase. And this is where you're gonna get like liquid extraction. Okay, just like in the previous, okay, in what we talked about so far, we don't want the two liquids to be mixed, right? We want solvent to stay by itself. We want diluent to stay by itself. We don't want them to mix with each other. We want only solute to transfer from the diluent to solvent. Okay, we don't want the solvent and diluent to mix with each other. But in this, like ternary system, three component system here, when they are partially miscible, you're not gonna get any extraction in this zone. Okay, you're not gonna get extraction in this zone because the two liquids, they are miscible to each other. They mix with each other. Okay, so in this zone you cannot get any extractions. You want your system to be in this phase. Okay, you want to be in this phase because in this phase, you're gonna get two phase. The two liquid will be separate. Okay, the two liquid will be separate. So we're gonna work with this zone here. Yeah. So yeah, like just like it say here, point M, point N, point N is a single phase. Is in a single phase. Okay, and point M is in a two phase mixture, and this is where we can work with. And you're gonna have, because we already decided that our chloroform is solvent and our water is diluent, right? So this side here, okay, the line on this side here is for the extract. Okay, the line on this side is for the extract, and the line on this side is for the raffinate. Okay, it's divided by this called plate point. Okay, plate point here. So on the left side is gonna be extract. It's gonna be for the solvent chloroform. Okay, it's gonna be for the solvent chloroform, and the right side here is for the raffinate. It's gonna be for the water side. Okay. And what else? And then there's something called conjugate lines. Okay, conjugate lines. Like they're also like two sides of the conjugate lines. Okay. Basically, the conjugate lines, they are related to the tie lines. Okay, to the tie lines. These are the tie lines. Like for the tie lines, each side, like this point and this point here, they are in equilibrium with each other. Okay, this point and this point, they are in equilibrium with each other, and this point and this point, they are in equilibrium with each other. Any of you guys still with me? and then this point and this point, they are in equilibrium with each other. Okay, so like from equilibrium data table, you should be able to make many tie lines. Okay, and these tie lines can help you construct the conjugate lines. Okay, and then uh, and then in the opposite way, if you have conjugate line, you can also like make these tie lines. Okay, so again, tie line they connect like two sides. Okay, on each side, like the side on the extract and the side on the raffinate, but on both sides they are like in equilibrium with each other. Okay, this they are equilibrium with each other, and you can you can draw the tie lines using the data from the equilibrium table, and you can also use tie lines to make the conjugate line, and the conjugate line can be used to form the tie lines. Okay, I really recommend you to look at this YouTube link here. It tells you how to plot the ternary phase diagram. Okay, like all these solubility envelope and conjugate line and tie lines. Okay, so like you really need to be able to draw these triangular diagram. Okay, like definitely on the exam I'm gonna ask you to draw these lines. So you need to be able to understand it. Okay, so let's consider this like counter current here. So you have counter current system here, and from this, okay, this is what actually happened in your process, right? You have like multiple stages, many streams going in and out from each stage, but then from this you can make like you can make an imaginary system. So this is like imaginary process. Okay, so this is your like imaginary process. Like from this, like like multiple stages, you can like remodel it. Like you find the imaginary process that represent these stages. So from this, you can imagine it into these two boxes here. Okay, and from these two boxes, you can like draw on the triangular diagram like this. Okay, so the problems like like you have E0 Rn plus 1 En and R1. These you need to be able to find from the information from the problem statement. Okay, the problem statement is gonna give you all these informations, and from this information you should be able to draw to indicate these 4 points. Okay, and when you draw the lines, like from these four points together, you're gonna get an intersection here, and this intersection point is M. Okay, and when you do the mass balance, around these M points, you're gonna get these equations. Okay, I'm gonna go over a bit fast here, but basically again, so you have multiple stages, the process with multiple stages, right? From this, you can like draw this imaginary process. From this imaginary process, you have like stream M. Like this stream M doesn't exist in real life. Okay, this like imaginary point, imaginary stream, but you can find it on the triangular diagram like this. Okay, using these 4 points, and then from this and do the balances, like balances on this diagram, and then you got this. Okay, and then you rearrange the equation, and then you got these two equations here to find the coordinate of point M. Okay, to find coordinate of point M, and then there's a special point. It's called delta point. Okay, like it's called delta point here. Again, I'm not gonna go into detail, but basically, yeah, this is a delta point. Okay, you can draw the lines, like from these 4 points, draw the straight lines, and it's gonna intersect at this point. This point is also again imaginary point. This delta point doesn't exist in real life, but it's gonna help you do the calculation. Okay, so yeah, this delta point here, and then from this data point, you can find the number of stages. Okay, so let me show you talk about this example here. So again, okay, let me go over the details. So from from the equilibrium data, you need to be able to draw the solubility envelope, something like this. Okay, and then from the solubility data, you can draw like many tie lines. Okay, many tie lines. Maybe something like this. I don't know, something like this. And then from the tie lines, you can draw like conjugate line. Okay, so in this case, the conjugate line is gonna look something like this. Okay, maybe the conjugate line looks something like this. And then you can use this conjugate line to help you solve this problem. Okay, so so the problem is gonna tell you this point here. Oh, sorry. So it's gonna tell you the information about this point here is because solvent is pure, right? The solvent is pure solvent, so no water, no water, no acid, only isopropyl ether. So you're gonna have only solvent here at this point, and also the problem gives you about the feed. Okay, the feed Rn plus 1. The feed point here, the feed, which is equal to Rn plus 1. And then the question tells you R1. Okay, R1 is going to be at this point. Okay, R1 at this point. And then you can use this formula here to find xm, the coordinate of point M. Okay, so point M is maybe something like this, like from this equation. Then you can draw, draw the line. Okay, draw the line. And then once you draw this line from R1 past M here, you're gonna get this point, and this point is gonna be your En. Okay, you're gonna get En here. Okay, and then from En, you can find the delta line by draw the state line. Kind of exaggerate here. Ah, I don't know if you guys still with me or not, but so okay, this is the delta line, okay, and okay, let me use this. So this is how you find. So again, first you know S, you know F, you know R1, and you find the endpoint here from this equation, and then you draw the line here to get En. And once you get En, you draw the lines, two lines here to get delta. Okay. Once you get delta, then you can find the number of stages. Okay. Right. So for so this is R1, right? You have to find this tie line. This tie line you use the conjugate line. This is the conjugate line. Okay, conjugate line to find the tie line. So the way you do it is to draw the line, to draw the straight the vertical line to the conjugate line like this. Okay, so this is how you find E1. Okay, so from R1 you find E1 here. Okay, using the conjugate line, you can find E1 here. Okay, so and this is the tie line that connect between R1 and E1. Okay, and then from this you can draw the delta point pass through E1 to R2 here. Okay, to get to R2. Okay, to get to R2. So this is your R2, and then you use the conjugate line to get to E2. I don't know if you can see it. It's a little messy here. Okay, so let me erase this. So okay, so like from R2 to the conjugate line, and then go to the left to this point. So this is gonna be E2 here. Okay, this is E2, and then you draw the straight line, you know, to E2 to get to R3 here. Okay, so this is R3, and again from R3 I go down to the conjugate line and go to the left. Okay, to E3 here. Okay, to E3, and then again I draw the line from the delta past E3 to go to R4. Okay, and then you keep doing it again and again until it pass, like from R6 it pass this En. Okay, it goes over En here, then you stop. Okay, like this point, this tie line from R6, you know, like R6, it's go it's kind of hard to draw. Okay, like this. Okay, yeah. So from R6 you get kind of E6 here, but this E6 is a little bit above. It goes further En a little bit more, like go beyond En a little bit more. Okay, then so you stop. Okay, so stage is about 5.8. Okay, it's about 5.8 because it's go the way I calculate it is, like, so this point here, this is E6, right, and this is E5. Okay, this is E6, this is E5. So En is right here, right? En is right here. So that's why I got about like 5.8, about 5.8 here. Okay, so that's why my final answer is 5.8. Okay, that's one way to do it. And the other way is to use the combination of triangular diagram and the Marquette field. This one you don't need no need for conjugate line, okay? But you use the solution envelope, okay? So you need to find the delta line anyway. But like from the delta line, you just like randomly draw a straight line, like, and then you put the Marquette diagram next to it, okay? And then just draw the point, this, and then you're gonna get this point here, and then you like you do it for many points. Like for example, maybe I draw another line like this, okay, and then so from this maybe, and then I go to this. Okay, then I got this point. Okay, and then maybe I draw many straight line. Okay, maybe at this point. Okay, so I have like multiple points here, and then I connect the dots. Connect the dots with the line, and then this is my overlapping line. Okay, this is my overlapping line. Like to get like multiple line here, maybe like to get multiple points here, and then like connect the dots. Connect between points, and then you get like overlapping line, and then you use this overlapping line to like find the number of stages. Okay, so this is like use a combination between the triangle diagram and the Marquette field, just like this. Okay, like this one, they try to use like different like use a combination between the triangle diagram and the Marquette field diagram to get this overlapping line. So this is the equilibrium line. Okay. Oh yeah. So this line, like this line right here. Oh, I'm sorry. So yeah, I say it wrong here. I shouldn't use like draw the steps here, because this one is y equal to xa. It's not equilibrium. Sorry, not equilibrium. So maybe, but this is the overlapping line, right? So maybe I don't know. Maybe the equilibrium line is something like this. Okay, maybe this is the equilibrium line. Okay, this is not equilibrium. Okay, so then when you find the step, it's gonna look something like this. Yeah. Okay, it looks kind of ugly a little bit like this. Okay. So this is how you do. Like you have to find the step. You just like before, right? When we want to find the number of stages, use the step between the equilibrium line, overlapping line. Not this line. Sorry, not this. This line is y equal to x. But you use the line y equal to x to find these. You use this line to find these points to form the operating lines. Okay.
นี่เราสอนเป็นเวลาวันนี้มันยากนะ
Okay, so yeah, and then so this is the example. Like you can use this technique also to find the number of stages. Well, actually, I plan. This because this chapter it requires a little bit of more explanation. So that's why I didn't get to show you my exercise. But maybe next time. Then next time I'm gonna show you the solution for this. Okay. So we didn't have time to show you my solution. So, but next time then. Any quick question? Anyone still with me? Actually, before we go, I wanna for next time, next chapter is chapter 10, right? Actually, I updated the slide a little bit, so you can get the updated version on the TU Moodle. Okay, like I fixed some errors, like just a little bit, not much, but like you should get the update version on TU Moodle for chapter 10. Okay, so I suggest you to go download it. Okay, anyone hear me? I assume that you guys hear me. Okay. Maybe next time when I talk about my solutions for the exercise, maybe you will understand it more. But I really